My friends, we're going to go through an onslaught of practice problems. It limits at infinity. We're going to go through so many exam problems, and we're going to look at it graphically as well so that you have this solid understanding on how to do any question like this on your exam. So let's begin. Okay, so we'll start off here. The limit as x goes to infinity of this fraction, polynomials, top and bottom, 2x squared minus 4x over x squared minus 5x plus 6. And don't panic. What we do, there's a shortcut method, and then the way your prof tells you, I'll show you the shortcut method right away, is you look at the term with the highest degree. Degree means the exponent, the exponent that has the highest number here. This is a 2. This beats this one, which is just a 1 here. So this is the highest degree. This one's the highest degree as well. And so at infinity, the term with the highest degree beats any other term. This is going to be so much larger than this term. Same as these terms here. They're essentially 0 as well. So it's really what we're looking at is the limit as x goes to infinity of 2x squared over x squared. So if you have 2x squared over x squared, you just cancel out the x squares, and all we're left with is 2. So the answer is 2. Now your prof may want you to solve this a different way using Hopital's rule. And Hopital's rule states that the limit as x goes to a of a fraction here of some numerator divided by some denominator, that's equal to the limit as x goes to a of the derivative of the numerator divided by the derivative of the denominator. If you haven't covered the shortcut rules of derivatives, then don't worry about this, but this is very common in limits at infinity, and this is Hopital's rule, the h, and if there is an s, both are silent, Hopital. So to do that, to solve this using Hopital's rule, we take the derivative of the top and the bottom separately. So the limit as x goes to infinity, this becomes 4x minus 4 divided by the derivative here becomes 2x minus 5. And we still have an x and an x here, so we take the derivative again. So this is equal to the limit as x goes to infinity of derivative of the numerator is 4, and the derivative of the denominator is just 2. So 4 over 2 is just 2. We don't have to plug in x or anything anymore. It just becomes 2. Now, your prof may say you need to multiply top and bottom by the term by the highest degree. So you're going to multiply the numerator by 1 over x squared. That's what the textbook says, or maybe your prof doesn't care. The bottom over x squared. And then when you do that, we get the limit as x goes to infinity of, so this is x squared. So we're going to feed this in, right? This gets fed into both of these terms. So we have 2x squared over x squared, which is just 2, minus, this is 4x squared over x squared. So that just becomes 4 over x. In the denominator, we're left with 1 because this cancels with this. See, we feed the chickens here, feed through. And this becomes 5 over x and 6 over x squared. And then if we apply the limit here, this term goes to 0. So that's fun. This term goes to 0, this term goes to 0, and we're just left with 2 over 1, which is 2. So the answer is 2. Now, if you want to see this graphically, this is pretty cool. I got this all set up. I graphed it here. I'm using Desmos.com online. This is what it looks like. This is the function in all its glory. And you see as x, this is the x-axis, as x goes to infinity, it's coming right on this line. And this line, if you can see it right here, this is 2. So it's getting close and close and close to 2 as it goes to infinity. All right, next one. Now we're going to do the shortcut method for these because they're my favorite. And notice that we have an x cubed here, x cubed here. Well, at infinity, this becomes 0, right? This becomes 0 compared to this one. It's negligibly small. It doesn't go to 0, but it's negligibly small compared to this one. So we're really left with x cubed over x to the 4th. So this cancels with these, 3 of these to these. So we'll have 200 over x. And we're essentially, it becomes the same as the limit as x goes to negative infinity of 200 over x. 200 over x. So as x becomes large, this whole thing goes to 0. It doesn't matter if it's negative or positive infinity, it's going to 0. It'll be negative on the negative side, but it'll go to 0. and I have it graphed here. This is the graph, and this is it. Kind of cool. If you might not have been able to guess this, but this x to the fourth term dominates. So we're going to negative infinity here. We're starting off at 200, but if we go over and over to negative infinity, see how this line, and it's just getting closer and closer and close to 0. It doesn't touch it because it's an asymptote. Next one here, this limit as x goes to infinity of the square root of x to the fourth plus 25 divided by 1 minus x squared. Now, we'll do the same thing here. This term becomes negligibly small, so we just ignore it when this becomes large. Same thing, this term becomes larger, this term becomes negligibly small, this becomes very large. So it's just like we're doing the square root of x to the fourth divided by x squared. And the square root of x to the fourth is x squared. It's actually plus or minus x squared, but we'll just keep the positive side. So this is like x squared over x squared, and this is a negative. So it becomes, I'll write it one more step here. This essentially becomes x squared over negative x squared, which cancels out, so it becomes negative 1. And if we look at the graph, I have it right here. This is the graph, and as we go to, where are we going? Positive infinity. So we go to positive infinity. It's staying very, very close to this line, which is negative 1. Sorry, it's kind of blocking here, but this is negative 1.5. This is negative 1. So it's hugging negative 1. It's not on negative 1. If we go close enough, it won't touch it, but very close to it. Okay, next one. So these are kind of fun, aren't they? They're really quick. It's a fun little game here. So as x goes to negative infinity of this function, we have a problem, right? We have like a large number in the square root. Imagine this is like negative 1,000. So we have negative 1,000, or it could be 10,000, a million, whatever, minus 2. This is going to be a negative number in the square root, which becomes an imaginary number. It's not allowed, essentially, for these limits, unless you're dealing with imaginary numbers. It's not defined here, so it doesn't exist. D and E, and if we look at our graph here, this is the graph of it, of our function, and just notice it stops right at 2, because when you plug in 2, this is when it's 0. If x is greater than 2, smaller than 2, if it's less than 2, then it's not defined. So we can't go to negative infinity. Does not exist. Alrighty, next one here, the limit as x goes to infinity of sine x over x. Now there's the shortcut method and there's the proper theorem way to do it. We'll do both. The shortcut method is, if you look at the numerator oscillates between two numbers. Sine x goes between negative 1 and 1, but the denominator becomes super large. It goes to infinity. And if you have a fraction with a very, very large denominator, then this goes to 0. That's basically all it is. But your prof probably wants you to use the squeeze theorem, and this is it. And please bear with me. There's a lot of words here, but it's not too bad. This is the squeeze theorem. If our function is f of x, okay, so our function is f of x, so this sine x over x, that's f of x here. That's f of x. And if that function is greater than or equal to another function, but less than and equal to a different function, so it's in between, the value of f of x, or the function that we want, is in between these two functions, then if this is true, and also what's true, if the limit of g of x and the limit of h of x as x goes to some number, if those are the same, say if this function g is the same as the function h, the limit of g and the limit of h here, if that's the same, then the limit as x goes to a of the function f also has to be L, right? Because f has to be greater than or equal to g, has to be less than or equal to h. If the limits of g and h are the same, then the limit for f has to be the same as well. So we'll go back here, sine of x, as you hopefully know, it goes from negative 1 to positive 1. That's sine of x. So the smallest that this function can be, this would be our g of x, is negative 1 over x, right? That's the smallest. And the largest it can be is 1 over x, because that's as high as sine x can get, the largest the numerator can get. And our function is sine of x divided by x. So our function has to be greater than or equal to the negative 1 between 1 here. So the limit of this function here, the limit as, I don't even know if I need to write this down, but I will, as x goes to infinity of negative 1 over x, I hope this is pretty obvious. You have a very large denominator, 1 in the numerator, -1 in the numerator. So this goes to 0 from the negative side. So this is going to equal 0. But also this one as well. The limit as x goes to infinity of 1 over x. X becomes very, very large. You have a huge denominator. That's going to 0 as well. So if the limit of this one's going to 0 and the limit of this one is going to 0, then the limit of this one has to go to 0 as x goes to infinity. So our answer, I'll make it here. Here's a big equal sign. The answer is 0. Here, and I'll show you graphically. This is pretty cool. So this is our function, sine of x over x. I apologize if this is small writing. And this is what the function looks like. It looks like a sine curve, but because of this x in the denominator, the sine function, it's damped. Like it gets smaller and smaller. See that? See how it gets smaller and smaller? And it still oscillates, but it gets closer and closer to 0. So as we go to infinity, it just oscillates closer and closer and closer to 0. And what's really cool is we can do the squeeze theorem here. So the lowest number was -1 over x. Remember, that's the smallest that the sine function can be. That's in purple. And the largest that our function of interest could be is 1 divided by x, because the highest that sine can be is x. And that's in black. So if we look, so purple is the lowest that it can be. And black is the highest our function can be. Our function is red here. And see, our function, it oscillates in between the purple and the black. And as we go to infinity, see what's happening? The purple and the black, they're kind of squeezing into the x-axis. And our function is oscillating back and forth between these two functions. So as we go to infinity, they all approach 0. And life is good. If 0 is good. Now for our next one, the limit as x goes to infinity of ln x over x. What's happening in the numerator and the denominator? Well, the numerator, ln x goes to infinity as x goes to infinity. You can kind of plug in bigger and bigger numbers. And x also goes to infinity. So what's happening is we have infinity over infinity, which doesn't cancel, right? Because one of these may go to infinity faster. Whichever one goes to infinity faster is going to overtake the other one. So in order to know which one goes to infinity faster, we need to know which one has the fastest rate of change, the greatest rate of change, and that is the derivative. And to do that, we use Hopital's rule. And the H is silent. Sometimes there's an S. That's silent as well. It's not Hopital's rule. Hopital's rule. So Hopital's rule says, just like before, the limit as x goes to a of some fraction here. We have some numerator divided by some denominator, function of each. That's equal to the limit as x goes to a of the derivatives of the derivative of the numerator and the derivative of the denominator. And this is valid. This isn't like the whole rule. This says if the limit of x goes to a of this if we get infinity over infinity or 0 over 0, we can apply this rule. Okay, so we have a situation here where we have an infinity divided by an infinity. So we're going to use Hopital's rule. So it's going to be equal to the limit as x goes to infinity now the derivative of ln x is 1 over x, and the derivative of x is just 1. If you haven't covered this yet in class, maybe just skip this example, or just use the shortcut method. Well, I guess you can't use the shortcut method. You'd have to know which one goes at a faster rate. Anyways, okay, so we take the derivative of this. Now this simplifies to limit as x goes to infinity of 1 over x. Now, it's super obvious, isn't it? We have a constant in the numerator, a denominator that's getting larger and larger. It's getting bigger than a bus. So we have a huge denominator. So this is definitely going to 0. And we could look at this on our graphing calculator. Here's ln x over x. And this is the function here. And it looks like a ln x, but the x is overtaking. And as we go to infinity, so we get farther and farther away, it does go to 0. And let me just show you what ln x looks like and also what x looks like. So ln x is the blue and x is the green here. And notice that initially it looks, our function of interest, which is the red function is the one we care about. That looks more like ln x because ln x has the steepest change here. But after a certain point, this is 1, after 1, the slope of x is greater than our ln x. So this green x, which is in the denominator of our function, that has a greater rate of change. So that's going to be that's going to overcome this change in ln x. So ln x doesn't change very much as x gets larger. See, the slope flattens out. But x continues to get bigger and bigger and bigger as we go to infinity. So the function ln x over x has to go to 0. Cool beans. So next one here, the limit as x goes to infinity of e to the x divided by x to the 12. Now don't panic here. Let's see what's going on. We can't divide anything out, right? We can't do that. When x goes to infinity, what's happening? Well, we have e to the infinity here. So this goes to infinity. And then we have an infinity to the power of 12, which is also going to infinity. So in this case, we also need to use L'Hopital's rule. So we'll take the derivative of both sides, top and bottom, sorry. Take the derivative of the top and bottom. And remember this limit. Don't forget that when we after the equals. So we'll take the derivative of e to the x. So that's our friend, e to the x. The derivative of x to the 12, we just use the power rule. So it's 12 times x to the 11. Okay, so this gets smaller. We still have infinity over infinity, right? So we take the derivative again. So it's the limit as x goes to infinity of e to the x. Now we take another derivative. So 11 times 12 is 121, x to the 10. Now we could keep going and going and going. This is still infinity over infinity. So we can use L'Hopital's rule again and again and again. But we can look at the pattern, right? And every time we take a derivative, the numerator stays the same. Numerator stays the same. But look what's happening to the denominator. The exponent is decreasing every time we take the derivative. So eventually, the exponent is going to drop to 0 if we do enough derivatives. Okay, if we do 10 more derivatives, it's going to drop to 0, which means we're going to have a constant in the denominator. So if we get to that point, once we get to that point, we'll have a constant in the denominator. It'll be like this. It'll be like the limit as x goes to infinity. The numerator stays e to the x because it's always e to the x, no matter how many times we take the derivative. But this exponent's going to go down and down and down every time we take a derivative. And we're just going to multiply it by this. It'll be some huge number. I don't even know what it will be. Well, it'll be 12 factorial, I guess. Anyways, this will go down, and then x to the power of 0 is just 1. So we have a constant here. Even though this is a big number, this goes to infinity. So the numerator goes to infinity, which means this whole thing has to go to infinity. And we can see that, again, have it graphed here for you. This is a really cool function if you look at it. So this is e to the x divided by x to the 12. And right at the origin here, we have an asymptote because we can't plug in 0 for x because the denominator we'd have 0 in the denominator, which means the function would be undefined. But if we scroll back a little bit, look what's happening here. There's not much activity just after, I guess, 1 or 2 or so. And then after around 40, the numerator starts to overtake the denominator. And we have this huge, huge increase. Between this region, it's like a tug of war. Who's going to win? Who's stronger, the denominator or the numerator? And it appears that the denominator is stronger. This is a lot larger. The denominator is a lot larger in this range, but then eventually the numerator wins. Next one here, the limit as x goes to infinity of x to the negative x over cos x. Now, this might look confusing, but if you rewrite this, it's actually not that bad. We just did an example like it. So this is the limit as x goes to infinity. Now, this negative, when you have a negative exponent, that means this factor or this part here goes to the denominator. Negative just means it's in the denominator. So we have this situation here. Now, if we plug in infinity, this denominator goes to infinity, but the numerator oscillates, right? Cosine oscillates just like sine, and it goes from -1 to 1. Well, we have this oscillating behavior. Therefore, we have to use the squeeze rule again. Good old squeeze rule. So the lowest that cosine can be, or this whole thing could be, is if cosine is -1. This function, cosine x divided by e to the x, has to be greater than or equal to -1 over e to the x. Our actual function has to be within greater than or equal to that, to the -1, e to the x, but it also has to be less than or equal to the maximum value that cosine can be, which is 1. So it has, or the function of interest has to be less than or equal to that. We can evaluate what the limit of this one is and the limit of this one is. Well, I'm not going to write it out again because I think you can kind of just see it. If we take the limit of this function here, if we take the limit as x goes to infinity, we have a constant numerator, but the denominator goes to infinity, so we have a super big denominator. So this whole thing goes to 0 from the negative side. And then same thing, same argument for this one. The limit will go to 0. This is kind of a bit street talk down here. But since both of these are going to 0, then this one has to go to 0 as well. And again, I'll show you the graph. This is really, really cool. Check out this function. So this is e to the -x times cos of x. And look what so cos of x is an oscillating function, right? It goes it's like a wave. But look what happens to the wave as x is negative. Like this wave is so big. If I scroll out, I can't even get to the top of the wave, no matter how much I scroll. That's how huge this amplitude gets when x is negative. That's crazy. But when x is positive, and we're going in the positive direction, we still have this wave, but the wave goes to 0 really, really quick. If we look at the smallest value that this function can be, that's -1 divided by e to the x. And the largest value this function could be is +1 to the power of e to the x here. So our red function, that's the function that we care about, the one in red, has to be in between the green and the blue, because the green is the largest that the value can be ever, and the blue is the lowest. And look, as we go to infinity, it's kind of getting squeezed in to 0. Okay, like a wrecking ball, we're flying through. I hope this is starting to get repetitive, because repetition means higher grades, right? The more you get used to it. Okay, the limit as x goes to -infinity of x times e to the x. This one is, well, let's look at the behavior of what's going on. This x is going to -infinity, and e to the x is going to it's going to 0, right? It's going to 0 because this is a negative number, and you have an exponent that's large and negatively. So we can look at this another way. Let's say the limit as x goes to, rather than -infinity, let's look at just regular infinity. And the reason I want to do that is because when we have a negative number here, a negative number in the exponent is like making this whole thing a fraction. So it's like making it like x divided by e to the x. Now, I put this negative here because we want to go to -infinity. But if I'm changing this to go to infinity, then I have to put a negative here. So if x becomes a very, very large number, it's a very, very large negative number here, a very, very large negative number. That means if we put in a positive number, this negative makes sure that it's still negative. And now, if we have a negative exponent, that means it's like we're in the denominator. So this is a positive number, which would make it negative overall. Let me know if that's confusing. I hope it's not. I hope this makes sense from going from here to here. Okay, so this numerator goes to -infinity. It goes to -infinity. And this denominator is going to infinity. So it's just like we have infinity over infinity, right? So which one's going to win? Now, it could cancel out and be 1, but probably won't. Let's do L'Hopital's rule, and we'll take the derivative of the numerator and the denominator. So this would be the limit as x goes to infinity of the derivative of -x is just -1 using the power rule, right? This is like exponent 1. 1 comes down, subtract from 1, it's 0. And then derivative of e to the x is our friend. It's e to the x. Now, the limit, this numerator is constant, but the denominator goes to infinity. So it's like we have -1 over a super large number, so it equals 0. And here we are, x times e to the x. As x goes to positive infinity, it kind of pushes off, but we care about going to negative infinity. So as x goes to negative infinity of this function, it's going to 0 here. So that's cool. Okay, all right. I don't have anything more to say about that. Okay, next one here, the limit as x goes to infinity of cos e to the negative x. Now, this one is crazy because it's we have a function inside a function. This is like a composite function here. But let's look at the behavior. So this is like 1 over x. So let's rewrite this. The limit as x goes to infinity, cos of 1 over e to the x, because that's what that negative sign means. And what's happening inside the cos? Well, as x goes to infinity, the denominator is going to infinity. So we have a fraction inside this cos. This fraction is going to 0 because we have a huge denominator, a constant numerator. One constant over a very big number becomes very small. So this is basically like cos of 0, essentially. And what is cos of 0? Well, cos of 0 is 1. You can plug that in your calculator. 1. So that's just going to be the same as cos of 0, which is 1. This is it. This is a sweet function. Check this out. Doesn't this look cool? This is really cool. Oh man. So this is cos of e to the negative x. It's kind of like this spring. So this is our cosine, and it's just pretty sweet. The wavelength just decreases, and it's kind of like expanding. But as we go to positive infinity, look at this. It merges, goes to 1 because cos of 0 is 1. So there we are. Cool. It's asymptotic there, but it approaches 1. Okay, the limit as x goes to infinity of x squared times e to the negative sine x. And this looks complicated, but let's not panic. Let's kind of break it down. We have this part here. It's like this is one function multiplied by another function. So it's like we have two functions here. And this second function, this is like a composite function. It's like a function inside a function. Anyways, we'll look at them separately. So as x goes to infinity, this x squared obviously goes to infinity as well, comes larger and larger. But this part here oscillates, right? Because sine x oscillates. Sine x is like a wave, and it goes between -1 and 1. So there's a range that this can be. It's it's squeezed between -1 and 1 for the value of sine x here. So we're going to use the squeeze theorem, and we'll look at this function here. This function goes between -1 and 1. Sorry, just for the exponent. So that means e to the negative sine x is going to go between negative e to the -1 and e to the -1 here. So this is just e to the 1 because negative times negative e. So it's going to oscillate between e to the 1 and e to the -1. E to the 1 is larger. So this is the smallest that it can be. So our lowest function will be x squared times e to the -1. And e to the -1 is just 1 over e, right? Because that's 1 over e. So if I could write this as x squared over e, that has to be less than or equal to our actual function, x squared times e to the negative sine x. I'm just going to get rid of this e to the 1, which has to be less than or equal to the largest that can be, which is this one here, e to the 1. So that will be x squared divided by e to the 1, which is just e. And the limit as x goes to infinity of this here, the limit as x goes to infinity of this one has to be infinity because we have a constant denominator and a numerator that just blows up. Same thing here. Well, these are the, wait a second. Did I do something wrong? 1 over e to the, what? 1 over e. Oh, this is just e to the 1. So this is not 1 over e. This is e to the 1. So this isn't 1 over e. This is x squared e to the power of 1, not -1. So this is not in the, this is in the denominator. This is not in the denominator. The limit of this one here as x goes to infinity, well, x squared goes to infinity. E is just a constant. So this is going to infinity as well. they're both going to infinity. That means this function here, the limit has to be infinity, has to go to infinity as well. Or the limit is infinity. The limit as x goes to infinity is infinity of our function f, if this is f. All right, and I have this function here, x squared times e to the negative sine x. And this is kind of cool, isn't it? Like this is our x squared. X squared looks like a parabola, but because there's this e to the negative sine x in here, we have this, still it has like a wave-like behavior. See, there's some waves going on. It's a parabola with waves because of this here. And as we go to infinity, I think this is pretty obvious. X is going to infinity very, very rapidly as well. So there we have it. It goes to infinity. All right, my friends, that's it. That was a total review on the limits as x goes to infinity. Check out my other calculus videos. Also, I have videos in physics and chemistry and whatnot, so check that out. Thanks so much for watching. If you got some value from this video, please consider giving it a like as it motivates me to make more. So thanks again, everyone. See you in the next video. Cheers.